Okay, you're good.
All right, so can I start?
Yep.
Yeah, okay. So I'm going to talk about this Nilpotence theorem of feminized functions today. It's I'm writing down one of its form called the ring spectrum form, and this is the one I'm going to sketch a proof for you. The statement is that if R is a connected ring spectrum of finite type, okay, and if I think about the Fourier map from F naught to MU, and I take an element alpha in my ring R star, then if the Fourier image of alpha is 0, alpha is nilpotent as an element in this ring R star. Okay, so in other words, the kernel of this Fourier map consists of nilpotent elements. Okay, so let me try to give you some background on why this thing is an important theorem. Okay, so let's start with the multi-Moore spectrum. So take P greater than or equal to 3 prime. So S multi-Moore spectrum and construction of atoms that constructed a family of maps. Those from -2 suspension of multi-Moore spectrum to itself. And what he showed is that if you apply complex K theory to this V1, then it induces an isomorphism on K theory. So this means that if I iterate map arbitrarily many times, I can get V1 to the n, which is still a non-zero map here. All right. Then you can basically do a position like this here. Mention so iterating this V1, if you change your n, you get an infinite family in the stable homotopy group of spheres. Okay, from here to here. This family has a name. It turns out to be the divergent part of the image of J. So if you draw it out, it's something like this. I'm going to draw the picture for P equals 3. So this iteration of V1 essentially gives you this part. Okay. So, but this thing depends on complex K theory, and you can ask, what if I do this? There is a similar construction. We define V of 1, the Toga complex to be the profiler of V1. And I think it's 5. Then there's a similar map, a similar infinite family from suspension to the current minus 1. V of 1. To V of 1. Turns out that this thing is also going to give you the family in the stable series. Okay, you can iterate this V2 map, and it's never 0. But the thing is that you can't detect this family. You can't detect that this is non-zero using complex K theory. Okay, so you can ask, is there something that knows about all these periodic families? Is there something that sees all the periodicity phenomena in this category of spectrum? So the theorem is essentially telling us that yes, MU is such a thing. Okay, so of course you can always use the sphere spectrum, but
do you know which other theories protect this V2 thing? If there's something better than K theory, but not necessarily MU.
The second morality theory.
Okay.
Yeah. So that's perhaps one reason that you might get interested in this, and some other reasons you might get interested in this is that the theorem applies many interesting results that we have seen so far. For example, this theorem implies the a version of the Nilpotence theorem. For all K's. Basically, this version you need to do a little bit more work, but this version tells you that the collection of all morale K theories together can detect Nilpotence. Okay. So, and from that, you get the system periodicity. Yeah. From that, we get the periodicity theorem. It actually turns out that this thing is equivalent to the Nilpotence theorem. Okay, but the way you prove this exact category theorem is that you prove this thing. Okay.
Is the fixed subcategory theorem equivalent to the KN version of the nilpotence theorem?
I think so. If this basically this one is more or less equivalent to that.
Oh, okay.
But it depends on certain, something like the possible class of BP is basically the truncated from Peterson plus the lower morale K theorems.
Right.
If you assume that result, then this and this are immediately almost the same result. So yeah, so I guess let me try to give you a sketch of proof of the Nilpotence theorem. This is a complicated proof, and first give you an outline. So the first the proof is essentially this. So you construct the filtration. Excellent. Okay, so the first thing is to filter S between S and M. You define the family called S and X of N. So how do you define the family? Essentially what you do is this. So MU is the Chomp factor. The identity map of BU. And so the BU is by periodicity theorem. The vector spectrum of M. This is the vector spectrum of the suspension of the loop space of SU. Okay. So and what you can do is you can take inclusion of the loop space of FUM. Okay. And then what this inclusion gives you is you have from here to here, and you can take the Tom fraction of this composition. So X of M. Define it as the Tom fraction of this composition. So maybe you want to think about this alteration. What is the homology of X of N? Turns out to be so recall that this thing is basically also these generators, but we have N. But here, yeah. Yeah. So it turns out that the filtration is not enough, and you have to filter this stuff. Yeah. So let's concentrate on this part. Xn goes to xn plus 1. So the second step is to filter this. Yes, that's right. Well, also need to p-localize. Going to do this for every time t. The same one. J. This X one. So how do you construct this this family? What you do is the following. So you think about omega of SU n plus one, and this thing SU n plus one acts on the complex vector space and C n plus one, and then particularly it acts on the 2n plus one sphere. So picture loop for this, but this thing has a name. It's called the James construction of the 2n sphere. Okay, so if you are very modern, this is basically the free U1 algebra on S2n. Okay. So this James construction has a filtration along with it. It's called the K step. K. Called K step of the James construction. And then you form this pullback. So this pullback is called as a detail. Now there is a composition from omega SUN plus one. Right? Over here. So this composition gives you a pump spectrum. The pump spectrum, okay, this thing is called okay. Then what you do is you take GJ to the F equation and so on. And there's actually a reason for this choice of the J minus one. But let me tell you a little bit about what this JK is. Okay, so
Is this thing already p local, or do you have to p localize or something?
no, you don't need to p localize until it's done.
You p localize after this, right? Okay.
Okay. Thank you for asking. Okay. So let me tell
Also, the map from SU to the loops SU to the loops S to the 2n plus one over there,
you,
is that like act on one or something?
yes. So basically, the fiber of this thing is omega SUN. If you neglect omega, this is basically constructing S2n plus one as a homogeneous space. Okay, of this thing acting on this with stabilizer at here identity being this. Okay. All right. Let me tell you a little bit about what is JK. So J of S2n as an explicit formula. This is, well, maybe J of X. Let's define it as omega sigma. This thing has an explicit formula. It's given by an infinite direct sum. N greater than 0. Okay. So what is modulo obvious equivalence relation, which is basically, you have this thing would be equivalent to the one without the star. This is the free, the space analog of a free associative algorithm. So what this JK is basically doing is that you take a truncation. Okay. All right. So that's the filtration, and I can tell you what this thing looks like algebraically. So I'm going to do it for this FK. All right. So look at the homology of FK. but you have so this is isomorphic to this guy that has a module over this ring, which is mind you isomorphic to X as well. Okay, all right. So can I erase the zero? Okay. So let's now see how the proof proceeds if I have constructed these two filtrations. Okay. So the first step is to jump from this infinite thing to some finite end. Okay. So if or remind you, alpha is something in R star. If this thing is equal to 0, then we immediately get that H subset star of alpha equals 0 for some large n. Okay, some large with finite n essentially because homotopy used with coordinates. Okay. So now we have arrived here, and we state the lemma is very useful. The lemma tells me that if there's an equivalence. If I have a inverse R with or E has to be a ring spectrum. R here is the spectrum. R here is the ring spectrum of our choice that we started with. Okay, and alpha is an element in.
Okay, how do we have a morphism from an arbitrary ring spectrum to a mu?
Okay, sorry. I'm stating this lemma. So E and R are some ring spectra. Alpha is an element in R star. Okay. And this doesn't have anything to do with mu yet.
Okay.
All right. This thing is compactable. There's only that. The Fourier image. So if you come back for this thing, it's telling us that if I look at this spectrum, east of R, there's an action of this is an R module on one hand, and also a ring spectrum on the other hand. And the theorem is essentially telling us that the action of alpha coming from the R module structure coincides with the action of alpha as an element in this ring. So from this, well, it's immediate that if we can have that MU about the amount of MU is equal to this, then we are immediately done by the lemma. Okay. But this turns out to be not true. In fact, the boss field class of that one strictly larger than M. But we can possibly hope for that maybe X of n, the positive part of X of n is equal to positive part of X n plus 1. But this thing turns out to be also not true. In fact, there are certain n's, there exist certain n's such that this thing is strictly larger than this. Okay. So what's
Question about the lemma. Alpha here, so this is an element of the monoid ring of the sphere spectrum.
yes.
What if HR star of alpha is nilpotent, but HP star of alpha is not?
What if H H what, sorry,
H R star of alpha
is nilpotent, yeah,
and R star.
and R, sorry, I don't understand the question. Cause I mean, alpha is something arbitrary.
Then how does it make sense to say H E star of alpha since that's the map from the Hamiltonian sphere spectrum?
Yeah, so this is basically the Fourier match. Okay, so if this makes sense.
Oh, I see.
Yeah.
Okay.
All right. So recall that we have reduced to some finite end here. Okay, and then, in other words, we are here. And now we have to do this reduction to some finite step again. So this is what they call step 2. Because that's H that's okay. But one may with 0. Yeah. Okay. Okay, so this basically reduces us from this G infinity to some finite J. Okay. Now, in order to understand that, in order to prove our theorem, all we have to do now is to make the third step. Let me write here, step 3. Which is really the miraculous fact that at this somehow microscopic level, you do have an equivalence of positive causes. Okay, so feature. That's not. Yes.
Can you explain why that thing like E tensor without finite star being trivial is just allowing you to like reduce to a finite space? Can you do it again?
Yeah, so how is this thing defined? Right? This thing is defined as the telescope. Actually, alpha bar. I'll hide the thing.
Yeah, like some suspension.
Yes. So this is basically inverting alpha and inside R. You part it like an R model, right? And then you tensor this sequence with E. On the other hand, what is this? This is giving you an action of alpha as an element in the ring tensor R. Right? So E tensor R is the ring spectrum. And the ring spectrum and the Fourier image this in this ring.
Yeah.
So the central claim of this lemma, which is not extremely hard, is that if you think about the action of HE star alpha in this ring, it's the same thing as the what E tensor R is also an R model. And because it is an R model, there is an action of alpha.
Okay.
The central claim is that the HE star alpha action on this is the same thing as the alpha action coming from the R model structure.
Isn't that like obvious or something? Like
I guess it's obvious, but
that is how
but
it's defined, right?
yeah, it's not difficult, but you need to. The thing is that you need to assume that it's the ring factor. Otherwise, this thing doesn't quite make sense.
I mean, yeah, because otherwise you have a map from sphere to E, right?
Yes. So this is an important assumption.
But my question was like, how did you reduce from X infinity to Xn? Like,
How did I
like how did that reduction happen due to this lemma?
This is not from the lemma. This is basically this reduction is basically the fact that homotopy groups can be used with colimits, right? Because X infinity is the colimit of all the xn's, and because I know that the image of alpha under Fourier is equal to 0 after I pass through the co-limit, I know that it must be 0 already at some finite n.
Oh.
It turns out that you can actually do this also to this.
Uh,
But why doesn't this work? Why do we have to prove this step 2? This is because these HJs, the GJs, they are not ring spectrum. So we can't use this lemma. So even if we know that the Fourier image of alpha in these GJs are 0 for some J, we can't conclude that this thing is contractible. And that's the reason we need to prove this thing. Okay.
Why are the XNs ring spectra?
They are actually E2 ring spectra. So if you look at SUN, right? SUN is proof. The loop space of SUN is going to be an E2 space. And basically, you can show that this thing is an E2 map. And therefore, after taking Tom spectrum, this an E2, this gives you an E2 ring spectrum. Okay. So yes, so SUN is a group, right?
Yeah, but it's not obvious that that's the same ring structure that's on MU.
Yeah, I agree, but it turns out this is true.
Okay.
All right. Yes,
That's defined as being a spectrum, right?
can I raise this one? Okay, I'm going to do this.
Yes.
Right. So start filling in some of the code. Okay. So do we agree that if we have step 2 and step 3, we are done with the proof of the theorem?
So yeah, another good question. So why do we care about that GJ tensor alpha star being trivial?
Yeah,
Like,
so
what does that give us?
right. So basically, if you know that this thing is trivial, right? And you know that this is the same boundary path, then by induction,
Oh,
what you get is that G0 and the alpha in your path is trivial. Okay. And then what this means, because G0 recall is x of n multiplied with p, and this is the ring spectrum, apply the lemma. The lemma tells me that the Fourier image is nilpotent. And therefore, by induction on n back to n equals 0, you get the case that back to the case that x of 0 is the sphere spectrum, and you get that alpha itself is nilpotent. Okay, right. So let's start proving step 2. So that we have this thing, and I'm going to only give you a very quick reduction. So I claim that this thing is done if no this lemma. True. Okay. So E2 debate. Important to E2 R debate. And vanishing lines. Also, one over 2 and 1.
Wait, what spectrum? This is the
Good question. There's a really x and plus 1 based algebra sequence. Turns out that this thing converges to the homotopy groups. Okay. So let's assume this lemma and let's see why this tells us that this thing is true. Okay. All right. So let's draw the spectral sequence for this. All right. This is minus this, I guess. S. And I have my alpha. My alpha is living somewhere over here. Okay, it doesn't quite matter where your alpha is exactly. And then I have these actually I wanted to get somewhere higher. So we have these vanishing lines, right? For any j. And if I take j very large, I can always make my vanishing line look large. Yeah. Take all that. Okay, so I can always make my vanishing line as low as I want. Okay, now let's take this. So hat means it's representative in the spectral sequence instead of the actual element. So let's take an arbitrary element. Let's take beta hat in my spectral sequence.
It's already been that NK advantage is above or below?
Above.
Okay.
So everything is concentrated. Right. So this is my alpha. And now what I can do to my beta is that I can multiply it by alpha. This is alpha and beta. This is alpha and square beta. Etc. Okay, but because I know that I have this vanishing line, I know that everything above this is 0. Okay, so if I choose my slope low enough below the slope of alpha itself, then I can always do this any dimension of my choice. And basically, if I invert my spectral sequence, what do I get? I guess that if I invert alpha hat in the spectral sequence, then because every element in the spectral sequence is nilpotent after I multiply enough copies of alpha hat, I see that if I invert alpha hat, this whole spectral sequence becomes 0. Right. So therefore, the homotopy groups, because the element spectral sequence is merging to the homotopy groups of the spectrum called as I have inverted alpha, this thing converges to the homotopy groups of alpha inverse alpha, which is 0. And therefore, this thing must be contractible. Okay. So this vanishing line argument basically establishes the second step. And
why do we need it for ESP2 of E2SD of GJ and not just E2SD of R10 of GJ?
This part is also written around with this. But I think in order to close that to you, actually what you use this. Oh, by the way, where did I use the condition that this is 0? I use it here. Okay, so if I don't know this, then it's possible that alpha multiplying element coefficient 0. No matter how low my slope is, it's not going to get killed by multiplication by alpha hat. But as soon as alpha has a non-zero slope, I can always choose my slope, vanishing slope to be below this. All right, so I'm not going to say too much about the proof of this vanishing line. If you look at Ravenel, he proves this by constructing a very geometric filtration, non-standard element filtration of this GJ and R. In the original paper of Ravenel's Hopkins, they take the different algebraic reducing to some mixed spectral sequence calculations. But I'm not going to say too much about it. Let me concentrate on the step 3, which is really the key step.
So you're saying that the reason for alpha having S greater than 0 is because
this is, but this is I'm looking at the xn+1 base answer. Right, so if this is true, then I know that it has at least 1. All right.
So is it true that G infinity is also a colimit of the GJs?
That's true.
That's true.
That's true.
So Gauss-Field, so it's essential that Gauss-Field classes are not preserved under.
Yes,
Cool.
otherwise,
Yeah.
we can, we don't have to do all this. We can just
Yeah,
compute
yeah,
the
yeah.
Gauss-Field class of atoms. And then everything's done. Thus, turns out this is not true.
Yeah, interesting.
All right, let me start step 3. So before starting step 3, we mentioned the result of Nishida, which is the predecessor of let's So the reason I'm mentioning this is that first you see that this is an immediate corollary if we establish the general implements theorem. But also the proof that Nishida gave for this thing actually is an important ingredient in the proof of the general implements theorem. Back to this step. Yeah, maybe I can explain a little bit about this after I start. Okay, let's do this. Let's do step 3. So it's a little bit complicated. Let me tell you the central thing. The central thing is the construction of a certain map. Of B. Let me tell you a little bit about how this B map is constructed. I'm going to give you a very rough sketch of the actual construction is. All right, let's take P plus 3 for illustration. And recall that H term is this. Drawing some one. Okay, so and if I take DJ, okay, it's DJ, then it's going to be 1 to n to the power of p to the j minus 1. Okay, so if I think about this, I'm going to pretend that GJ itself is a cell. Okay, and what does GJ plus 1 look like? If I think about GJ plus 1, it's going to be something like this. Okay, because if this thing is a whole cell, then its dimensions 1 through 2n times p to the j minus 1. That's 0 through 3n p to the j minus 1. Then what is this? This is 0 through 2n p to the j plus 1. So basically, this has 3 times more generators than this. If GJ is a single cell, then this thing has to be 3 cells actually. Okay. Well, write down the dimension. 0. Actually, 2n. Sorry, what's the dimension? Okay, 2n p minus 1. This is 0. This is 2n p minus 1. And then I can think about the inclusion of the bottom cell into this. And I can take the co-kernel, the co-fiber of this time. This is what this is 2. So what is this thing? This thing turns out to be the thing we wanted to be in this suspension to MP to the day. And minus 1 to the day. Okay, so if it is suspended, it is desuspended down to dimension 0, then this is the thing you might guess it to be. Okay. Now, can you erase this? Now, equipped with this, you can start to draw this diagram. By G to H plus 1. Map it to this thing, which is my F suspension. Okay, so, but also then include your F suspension of F into another quantity plus 1. So this thing maps into this, and the whole composition is for R. Okay. And if you look at this is 0, here to the day, if you look at the co-fiber R, you find hey, what does K look like? K looks like something like this. This is a cell. This is a cell. Okay, this is in dimension 1. This is in dimension. This is in dimension 2 and K plus. So this is my K. And now what is B? B is essentially this much. And so if you look at suspension minus 1, okay, because something with a bottom cell at dimension 0 and the top cell at dimension 2 plus 1 minus 1. And if you think about the attaching map, this is a GJ cell, this is a GJ cell, and the attaching map has to be of this form. Okay, attaching map. Okay, so basically from this construction, we immediately see that HFT star of B must be so must be 0. Okay, plus this attaching map, and basically for dimension reasons. Now, this construction gives you something else. So, if you look at the co-fiber sequence associated with R, the co-fiber sequence of R. If you look at the co-fiber sequence of B, that's where you need another ingredient, which is basically this filtration. You look at all these three and you realize that the co-fiber of each of these is a copy of GJ. And so if you have these three sequences together with some general lemma about field classes, you're going to be able to conclude that field class of GJ sits between two things. Plus the inverse of J. Okay, so now we are reduced to, so it just suffices to show that this thing is critical. Okay, suffices to show that B is nilpotent. I'll give you that. Therefore, it's popular class is true. Okay, so we are reduced to proving reflect. Yeah. And there, this is where the argument resembles the original argument of Nishida. Okay. Let me give you a sketch of the final set. So how do you prove this? This is going to be, I'm going to draw diagram. So we call that DK. It's going to be the pullback. Okay. And one is the pullback. One. Pullback. This is how we define the state PK minus one. Okay. And now the reason we're choosing this P to the J minus one is that in this special case, you have something that allows you to extend this bottom sequence further to the right. This is something if you're familiar with the EHP sequence. This allows you to extend it omega s 2m p to the similar here. Now, if you look at that, and then the left, omega 2. And it turns out that if we concentrate on this, turns out that you can think of it as some sort of homogeneous space, in the sense that there's an action of this double loop space. As you pass the spectra, you get something like this. Okay, get an action like this. But this thing, in fact, splits into direct zones. I'm going to use this chart. Notice that this is a 3E2 algebra, and turns out that the decomposition of this 3E2 algebra has an explicit description. So. Okay, so the only thing we are going to use is these PIs. Turns out that this is the key of the key set. You have this factorization. Where you iterate of B I times. Recall that we have this action. Extension utility. Plus omega 2. One. Here's the factorization. There's a map sending. There's a map between each of the BIs. So there's a map called L that between each of the BIs, and it turns out that 0 is equal to the here fraction. this is how this map is constructed. Okay, you iterate your L items, right? Starting from S0. And it turns out the problem is the same. Okay. So with this diagram, we found this order diagram. Here, this method to repeater. This is L. Okay. So now what you do is you take the colimit of this line, the colimit of this line, and what you end up with is taking colimit. Here. Okay. Bottom line is basically B inverse. Okay, and then you convert B on this and this. This is already inverted. So what you get is inverse G big. So you have what is this composition? This composition is the identity of the inverse Gj. But we have shown that you call it the effect of B on 1P homology is trivial. So this thing is trivial. Therefore, the identity of the inverse Gj is 0. And therefore, B inverse Gj itself must be trivial. Okay?
Yep.
So that's what kind of the whole group. And it is this factorization that's very similar to the original argument of Ishida. In fact, this DI has a name, it's called a Brownian perspective. So the key to the whole proof is this factorization through Brownian perspective. That's what gives you the result. Right?
All right. Thanks. Questions?